So I'm going to talk about Laplace Transform. There has been some introduction in another module. Am I right?
Maths, yeah.
Maths. Okay, so I have some notes here. I'm going to follow my notes because there are some complications that I don't want to miss any step. Anytime you find it difficult and you want me to stop and explain it, because it has some roots in the maths that we had in the past or in high school. So you're familiar with Laplace. It is a way of solving differential equation related to what we do here in this module. The way it works is we take the function in time and we convert it to a domain, and then we solve it when it is in simplified format in S domain. And then we do the inverse transform in order to find out the real answer. Okay? So when I say real, the reason is because we are looking into imaginary domain. And it is important to look into that because in most cases, when we are looking at mechanical system, we are looking at some parts of that mechanical system that has uncertain movements. One of them is oscillation. Okay, the spring that is attached to mass, or a dashpot, or something that is oscillating in general. So when we are looking at oscillation, remember we were looking at this response of system, which had initial value, it had transient response, and then it had steady state response. Do you recall that? Yeah? So if we had let's say spring and then dashpot or damper and then connected to mass, and then we had this initial force to move the mass. So the way that the system is going to respond is going to start from this initial value, okay, the initial state that it has, and then it's going to move toward this oscillation state. If I want to plot it, remember how the plot would look like? It's going to have a little bit of exponential, and then it's going to have oscillation, and it's going to settle down. Yeah. Exactly.
Yeah.
So we are going to have this initial state, and then we are going to have this oscillation. And then at this stage, we are looking at steady state. We care about each of these because it is important when we are designing our system and when we are troubleshooting our system. Now, how a Laplace transform is going to help us to do this is, once in a while we have a system and we want to know how exactly mathematically the oscillation can be understood, how mathematically the steady state can be determined, and how mathematically the initial state can be determined. So Laplace is going to help us doing that. So we are going to write the force here in form of time. Yeah, so far everything that we were doing, we were looking at time. Remember when we were doing derivatives, integrations, we were all looking at time, and that's why we were looking at dt, right? So whenever we were looking at that, we were looking at the function of t, function of time. Now, Laplace transform is going to take that, move it to another domain. We call it S domain. So what happens in S domain, we have capital F for our function, and we are going to use S variable. So this S variable is going to show what's happening in S domain. This S domain has that imaginary part involved, which is looking at the oscillation. So if I want to write the S itself, I can write it like, what is that Greek letter? Alpha.
Is it 0 plus j or so, isn't it? Or
yes, we have this j,
yeah.
and then what's the next one? Sometimes we call it omega.
Omega, yeah.
Yeah, let me check my notes if I'm using the same. Yeah, okay. So this part is going to be our real part, and then the second part is going to be our, what is it? Imaginary. Am I writing the English correctly? Is double M or no, imaginary? Yeah, imaginary part. Okay. So when we want to plot any value of S, we are looking at vectors that can be displayed here with having the value of S and J. Sorry, yeah. Yeah. This is the alpha, sorry. Yeah. So if I end up with S is equal to 1, I am looking at here because I don't have any J.
Is that, sorry,
yes.
alpha there?
Yes.
Sorry.
Yeah, it is alpha. If I look at, let's call that S1, let's call S2 as 1 plus J, where that dot will be? It's going to be here, right? What about S3 is equal to 1 minus J? It's going to be here, right? So this will be S2, this will be S3, and that one is S1. We can also move to other sections. How I can move here if I have negative value there. So let's say if S4 is minus 1 plus J, I'm looking at somewhere this side, and that will be my S4. And if I'm looking at minus 1 minus J, I'm looking at somewhere down here. Is making sense so far? Okay, so this is our S domain. Now let's take a look at the mathematics of the function f and how we are going to convert the target into this. I moved to the other board and I moved the camera. Hopefully it can record things that I'm explaining. Okay, so if you're interested to know a little bit about the history of Laplace, I have a PDF file on Brightspace that you can read. It's interesting to know where the name comes from. Yes. And when we are looking at fs, we are looking at this integration from 0 to infinity, and we are looking at exponential here. Anyone remembers what is the exponential? It's minus st dt. Okay, there is something missing here. Plugging in the ft. Okay, so this is the basic form of Laplace transform. So what does it mean? It means that I'm taking my ft, which is the function in time, and I am doing this integration, and I have exponential component here. So anyone has done integration from 0 to infinity before? Yeah?
I was doing this last year.
Yeah, how do we do it?
Integration with parts.
Yes. And that means that we do what? Can you help me write it down? So when we have integration from 0 to infinity, we are doing limits. Okay? Now if I replace infinity with letter h, and I imagine that h is going to be infinity, I have limit of my exponential, my function, and that's how we write it. And then how we operate this limit?
So is it like the one in the math tables, and then you just input 0 to infinity on.
Yeah, we plug in the values.
Yeah.
And then there is a subtraction, right?
Yeah.
So we plug in the value on the top, and then we plug in the value at the bottom, and then there is a subtraction. Okay, so that's how we are going to do. Now I want to rewrite it again. This operation can be written with this operand. It's a little bit curly L. So if I say that Laplace of function f of t is equal to capital F of s. So here, time domain, here, s domain, right? I'm going to derive it for a couple of functions, and then we see how we can use that for the mass and spring example. Yeah.
When is the final quiz?
The week after Easter when you come back. The same time as lecture time. And it will be online quiz. Now let's imagine our function of time is actually exponential itself, and it is e power of lambda t. Now, if we plug that into that equation that we have there, we want to calculate f of s, which is going to be lambda of, not lambda, sorry, Laplace of e to the lambda t. And that means it is going to be integration of 0 to infinity of e minus st and e lambda t dt. So here we have multiplication of exponentials, and we know from math that whenever we have a power e to the a multiplied in e to the b, how we can write it? Because they are multiplied together, we can write 1e, and then we can write a plus b. Yeah, everyone remembers that? We're going to use that concept, and then it's going to be integration 0 to infinity of e, and then if I get the minus out, it's going to be minus s minus. So if I multiply the minus, it will be minus s, and then the lambda will be positive. then I have dt here. Now, we are going to create new variable, and we are going to substitute that inside this in order to solve it. So there is one t here, I missed it. This value here, I'm going to draw a circle around. I am going to call it u. I call the entire part. Now, if I do derivative on this u, I'm going to have du respect to time. If I do respect to time, I can consider all these as constant. So it will be like derivative of x in time if my x was, let's say, a constant, 2t. How the derivative respect to time would look like? The t drops. We have only the constant. It will be the constant 2. So the same thing applies here. So if I'm doing the derivative here, the t drops and I will have the constant remain. Yeah. And then I want to get dt out of here, to substitute it here. So what I can do is I can reverse both sides and then do a butterfly multiplication. So I can write dt. I keep the minus and s. Is it okay? All right. So I have this, which I'm going to substitute here. There. Okay. So now this part, if I rewrite it again, I call it u. So it will be e to the u. And then if I substitute dt, it's going to be minus 1. I missed something here. Nobody noticed. What happened to my du? Okay. So I'm going to have s minus delta multiplied in du. What is u right now?
U is minus s minus lambda.
Yeah. Yeah. Okay, now if I want to do this integration, it goes back to, what was it called? Taking limits, yeah. So I'm going to do the limits. It will be minus 1 s, and then there will be here. What are my values that I'm plugging in? It's 0 and 8. Now, how I do plugging in? I plug the infinite first. I keep the s minus lambda. The only part that I am plugging in is u. So it will be e to the infinite.
0.
Yeah, and then subtraction e to the 0. Yeah, so what's happening? When you have exponential to infinity, what's the value of that? Anything to the power of infinite will be 0, right? Yeah, it is 0. And then the exponential to the 0, whatever we have to the power of 0, it will be 1. So there is this minus sign here to the 1 that will come out and cancel that out. It will be 1 is minus. So what does it mean? It means that, if I get rid of that for a second, it means that Laplace transform of, what was the initial function? E to the lambda t is equal to 1 over s minus lambda. Yeah? So the same way, common functions can be calculated, and then we can have a table of Laplace values for common functions and forms that we often use.
Can you use other forms of integration? Do you just stick with the integration with parts?
Well, sometimes we do the fractional transform. Yeah. Sometimes we have to do that. I have another example. Let me see which one I want to do. Yeah, I think I do one more example, and then I move to the mass and spring. So before I move on, let's look at this for a second. Let's see what that means. Take a look at the lambda, lambda t. What kind of functions we can imagine that looks like that? It can be e power 2t or e power 3t. That lambda can be any value as long as lambda is greater than 0, right? Because here there is this condition that we want to fulfill, and we want the lambda to be positive, and we want this to be non-zero. Okay, so we want the s minus 1 to be greater than 0. All right. So what happens if we consider some values for lambda? One value that I can think of, let me see what I have here. Is 0 itself. That makes it interesting. So here I would say greater or equal to 0. And then if I put lambda is equal to 0, what happens? My function e to power of lambda t will be e power of 0 or 1. That makes the Laplace interesting because will be Laplace of the value 1, and that will be s minus 0 or 1 over s. So we have another Laplace added to our table, and that is Laplace of single value, constant value of 1, which is 1 divided by s. So similar way, we can come up with different ways that we can look at Laplace transform and then we can use that for differential equation. Let me see if I want to do the next example, or I might leave it for you to study yourself at home. I think I'm going to leave that for you to study at home, and then I move directly to the example that we have, because the relationship is very important, how we apply the Laplace transform to our programs, our mechanical systems. So imagine you knew everything by this point. Was a review. Am I right? Pretty much a review. Okay. Okay, looking back at our spring dashpot mass system. So if I want to write the function in time, how that looks like? We had the acceleration, remember? Yeah, that's the MA. And then we have, where did this part come from? Dashpot, yeah. And then we have kx, yeah. X itself can be function of t, so I can replace it with x of t. Okay, just remember that. When I'm looking at function of t, I have time incorporated here, I have time here, and I do have time here. All right. What does it mean? It means that over the time, the operation of the system varies. Right? The displacement varies, and we know what happens. We pull the mass, and then the oscillation happens, and then settling down happens, the steady state happens. Now, if we want to do the Laplace, we are going to apply Laplace to both these sides, and it's the way that we apply it is similar to derivative. So we do the Laplace here, and we do Laplace to that side. Now, if I write that will be the conversion of that part, and then I will have why did I write it this way? All those x's, they are being converted to s, and each of those, they can be found from the table of Laplace transform. So each component has its own equivalent in S domain. So we are in S domain right now here. When I say S domain, that means that I'm looking at S instead of time. Yeah? All right. Now, if we solve that, we are going to end up with x of s in a form. It's going to have a form here that has some constants, basically. At this stage, we can plug in our initial values. Let's imagine this system is working based on these assumptions. So our mass is 1 kg. The force, this force, I should probably write it F, is 5. What's the unit of force? Newtons. Yeah. And then the constant C, let's imagine it's 4, and the constant K, let's imagine it's 5. Now, if we plug that in, we're going to have something like that. There we go. It has very interesting look. We can
C for C, that's the dashpot.
yes.
Does that have a unit, or is it just?
Well, they are the constant units based on how they are made. Okay, they don't necessarily have units. Both of them, C and K. Yeah, they are related to their manufacturing, their sizes, and the material. So here, if I'm looking at this part, I can split them. Anyone knows how to split this?
So partial fraction is the next.
Yeah, that's where the function comes. Let me use another color.
So you factorize the quadratic equation, is it?
Hmm?
You factorize the quadratic equation, is it?
Yeah, it is going to look very interesting. It's going to look what is it? Plus 2 minus j, and then s plus 2 plus j. Where did this j come from? That's the imaginary part, right? Now we want to understand what does this mean. This is the S-domain solution. And whatever makes this answer infinite, it's going to be called our poles. Have you heard that word before? Poles.
Poles,
Yeah.
poles.
All right.
Yeah.
So I'm moving back to the other board.
Do you mean the input signal?
Let's continue and see what exactly they mean. We want to have this x of s working fine, right? So we have this constant on top, and we have something going on here. Okay, whatever going on here, if they go to 0, I'm going to have trouble, right? I'm going to have infinite value for that. That's not what we want. So we want to avoid that. So I'm going to make sure I'm checking all the possibilities that make this go 0. And that means I'm going to check individual of that. So based on this condition I have here, I should put this equal to 0 and check the value for that. I put this equal to 0, check the value for that, as well as this. So the simplest form would be S if S itself is 0. If S is 0, can I plot it? Where is it? 0 plus 0.
Yeah.
That will be the origin. Yeah? That's one of my poles. Poles. Yeah? How about the other one? s plus 2 minus j is 0. That makes s is equal to minus 2 plus j. Where on the board is that? Minus 2 plus j. Yeah, if that is minus 2, that will be my second pole. I have another one. I put that one equal to 0, that one equal to 0. The other possibility is s plus 2 plus j is 0. And that makes s equal to minus 2 minus j. Where about that pole is? If I go minus 2 and I come down minus j, that's where we are. Okay? So that's P1, pole 1, P2, pole 2, and P3 for our third pole. Yeah.
See where you set s is 0 at the very start?
Yeah.
Do you always do that, or is that?
It's because what we have here.
Oh, okay.
Yeah.
Yeah.
All right. Now, we know those are our poles. They are going to make trouble for us here, and we want to keep the system going well. Now, we want to see if I put those values, how my s is going to look like. Okay, so we are going to substitute those values and see how the s looks like. I keep this down here. I have two ways of doing it. I have it on my notes. Later on, I let you scan my notes. The easiest form would be if I write my x as 3 different fractions, and then I give each of those, what was this one? S plus 2 plus j, s plus 2 minus j. We know that when we want to split fractions like that, we are going to look into something that is going to be multiplied on the top, right? If I call the first one a, and the second one b, and the third one c, now I can calculate a, b, and c. The way that we calculate a is we plug the value of s in case that s is 0. So that will bring us to this equation again. I am going to write it. Did I miss something here? Sorry, let me check that. I think I missed something there. No, I'm right. Okay. So I have 5 and s. If I write the initial form of that, would be s2 plus 4s plus 5. You can also write it this way. that's okay. And then I'm multiplying it in S. And then I plug in the S is equal to 0. How much is that going to be? It's going to be whatever is going on here, and then multiplied in 0. That's going to make it 0, or no, I'm wrong, sorry. This S here cancels out with the S on the top, and then I'm going to have the 0 plus 0. That will cancel out, and then I have 5 over 5, which is equal to 1. So I know the value of A is equal to 1. Now we want to calculate B. Use another color. Oh, but B is going to be S plus 2 plus J, X of S. By plugging, the value of S is equal to minus 2 minus J. And that is going to give us this equation here. I'm going to have 5 in S plus 2 plus J, and then I have S plus 2 plus J, S plus 2 minus J, and then this guy here cancels out with this one, and then our B is going to look like minus J minus 0.5. Now we want to calculate the value of C. C is going to be S plus 2 is J, X of S, plugging in the value of S is equal to minus 2 minus J, and that is going to be equal to the similar way. It's the other one is going to be cancelled out, and then that one stays, so it's going to be positive J minus 0.5. So that means that C is equal to now, if we put all of this back into this equation of here, what will happen? We can have the answer in S domain, and then we can do the inverse operation to find out the answer in time domain, right? What is A? A is 1. What is B? Minus J minus 0.5. And what is C? Plus J minus 0. Okay, let's take a look at this and see what does this mean. Okay, so we have these three sections that are making our S. With current condition, we can convert it directly to time, because we want to find out how do they look like when they are in time domain, and how exactly that is related to the transient and the steady state or initial value of our system of them. So if I do the reverse from the table again, I can write the x of t. So this is going to be reverse transform. That is going to give us, this is familiar. We have done it, yeah, half an hour ago. Yeah, and we call that function as unit. And then we can do some mathematics here to make it look more like what we are familiar with. So if I write a little bit of mathematics that we use, minus j minus 0.5 exponential of 2 plus jt plus j minus 0.5 exponential of minus 2 plus jt. That would be the equivalent. And we know that exponential to jt is equal to cosine of t plus j sine of t. Yeah, that's how we were plotting it. Now, if I do write this here, it's going to be ut so that's going to come here, and then I can rewrite that, and I also factorize. So I will have 1 minus exponential of minus 6t and cosine of t plus 2 sine of t multiplied in unity. So what is this unit?
That's UT, isn't it?
Yeah. Yeah, we call it unit function. Yeah. And normally this is referred to the initial condition, initial state of our system. Now, this is the result in time domain. Okay, so it does have sine and cosine, yeah, and it has exponential. So we are looking at transient response. When we plot that, it's going to look something like this, right? Now that would be our transient response. And then for determining the steady state, can anyone guess what should we do?
Did you convert CUT on the second line? Did you convert that into after the end of the bar? Sorry.
Oh, sorry. Yeah, my bad. Yes, thank you.
Did you convert that into cos? No, look, next line.
I factorize it,
Yeah,
and that's how I
factorize it.
have this one here.
I get you, yeah.
Yeah, all right. So if I want to calculate the response when I am at my initial state. When we say initial state, it means that I am in time 0. That would be initial state. So if time is 0, what happens? What will be the value of that? Yes. Everything is going to depend on this. Yeah? And if at the start nothing is moving, that's going to be 0. So my whole x of t will be x of 0, and that's going to be, it does make sense because at the start nothing is moving. So my x, which was my displacement, should be 0. Yeah. What about this steady state? So this was the initial state. How about in the future? When bouncing is done, the transient time is passed.
So you just input your time,
Yeah, so what is that? What value should I put for steady state? Yeah, do we know that? We don't know, right? Yeah? So if we don't know, we are going to put infinity. Or we probably say going to infinity. All right? So in that case, what will be the value that I have? Mhm. So let's take a look at here. What do we have here? If time is infinite. Again, if I'm looking at this unit function, right?
Can you cause infinity?
Mm-hmm.
If you put infinity in as t, what is cos infinity?
Yeah.
E to the power of ut is multiplying the cos of sine. So if that's e to the power of infinite, it's 0. So then you
So if I have e to the infinity,
yeah,
what is the value of that?
0.
Why? Something to the power of infinity.
Oh yes, it's 1.
Is it 1?
Yeah. Something to the power of infinity. It's infinity, right? Isn't it? 10 power infinity will be infinity.
Yeah.
But the thing is, we are exponential power of minus. Power of minus means 1 divided with infinity. And that means 1 divided by infinity. And that makes it 0. Yeah? So this entire part is going to be 0. So I will have 1. So when time is 0, when time is infinity, e minus infinity will be 1 over e power infinity, and that makes it 1 over infinity equal to 0. And that brings the x of t to 1 minus 0, which is 1. So x of t in a steady state value is going to have the value of 1. Let's draw the transient response again, based on what we learned here.
So would it have like a unit step signal or?
That unit can vary.
Yeah.
We can assume it is a step, and that means that we pull that and we let it go.
Yeah.
Okay, but there might be other systems that u is not necessarily a step function.
Yeah.
Okay, so remember when we were looking at the transient response and then steady state response, right? Here in this case, we know that our starting value is 0. And we know that our steady state value is unit 1. Yeah? Okay, so we are reaching there with this function, which is going to be a combination of sines and cosines. So it's exactly going to be the oscillations that we were talking about. But by the time that we are far in the future, we are settled down to our value 1. So that would be this steady state response. That this 0 would be our initial value, initial state. And what's happening here in the middle, the oscillation, which can be defined with this, yeah, that is transient response. That's how you apply Laplace for transient. Transient means by the time that you're oscillating, and you're trying to settle down in your steady state. Okay? Interesting? Okay. That's all I have for today.